Good morning, class. In the last video, we ended up making an indicator with cabbage and using it to test the pH of some solutions at home. But what are indicators? And today we're going to learn how they work. So let's go ahead and continue on with this. What are they? Indicators are chemicals that change color depending upon the pH of the solution that they're based in. They're actually weak acids or weak bases. Now, what does it mean to be a weak acid or weak base? It means that it doesn't fully dissociate when it's put in a solution. Remember, dissociation is how something separates into its ions or separates into its parts. So weak acids and weak bases only partly separate. And an indicator will have a different color depending upon whether it has an attached ion or not. So if we took an indicator, for example, our good indicator litmus, litmus would come in two forms. There'd be litmus without an H, and there'd be litmus with an H. Litmus is actually a weak acid. We can see litmus with an H is red, and litmus without an H is blue. These are just the way that these chemicals react with the light based on their chemical structure, or in other words, having an H or not actually changes how it reacts with light. Now, why would it change color in an acidic or basic solution? Because indicators want to reach something called equilibrium with their surroundings. Let's take a look at what happens when it's in an acidic solution. When litmus is in an acidic solution, we see here that there are some lit minuses, there are some H lits, right? In other words, we can see that this is a weak acid. Only some of the litmuses have dissociated. Some of them are still bound together, and some of them are dissociated. When they're together, if you have half red, half blue, it's neither red nor blue, right? So in an acid, it has to be red. Why does it turn red? Well, let's think about this. What is in an acid? Acids always have lots of H plus ions. So I'm going to write in some free H pluses hanging around here. Now the litmus is going to look around itself and say, whoa, there are too many H pluses around here. So what it's going to do is it's going to try to grab any H pluses it can. What we see here is that the litmuses that are not bound to an H, not bound to a hydrogen, are going to grab up the extra hydrogens that are sitting around. Now, what happens to this litmus when it's in a base? As we see over on our right side here, this litmus is again half red, half blue because it's a weak acid. It's put into a basic solution. What free ions are floating around in base would be OH minuses. And in this case, we see that the litmus will look around itself and say, oh no, there are not enough H's in this solution. If there are not enough H's, I need to give away some of my H's to find balance with the other solutions. Hopefully we can see how this makes litmus turn red in an acid and turn blue in a base. How do we use indicators? Different indicators reach equilibrium at different pHs. This means they change colors at different pHs. So through some testing, we can make an indicator table that tells us what pH an indicator will change color in. Let's try an example. So we have a mystery solution that has a mystery pH. We need to use a variety of indicators to determine the pH of the solution. Now it's a mystery, but I'm going to let you in on a little secret just so you see how this process works. Secretly, I'm going to tell you that the pH is 10.5. Now let's pretend that we don't know that. We're just going to secretly know that. So mystery solution, we don't know what it is. What we're going to need to do is we're going to need to test it. So first thing that most people test with is litmus. When I throw litmus into this solution, the litmus turned blue. Well, what does blue litmus tell me? Taking a look here, litmus in the blue range is bigger than pH 7. So that means I have a pH that's larger than 7. Well, that's a good first step. but that doesn't really tell me that much. That narrows down only half of the situation. So I'm going to try something that'll tell me more information about a base. So I'm going to try phenolphthalein here. When I throw it into phenolphthalein, the solution turns pink. What does pink tell me in phenolphthalein? Oh, well, that means that the solution is above pH 9 or 10. So the solution has a pH larger than 9 or 10. That narrows it down some, but it's still not quite. Because is it 13, 14, 15, or is it just 11 or 12? There's still more for us to narrow down. So we need to do another test. Test 3, we're going to use indigo carmine. When we put it into indigo carmine, it comes out as blue. When we take a look at our indicator table, blue indigo carmine is here at 11 and smaller. So this tells us that the pH has got to be less than 11. Well, let's bring all of this information together. I know that the pH is bigger than 9 or 10 and smaller than 11. This tells me that the pH of our mystery solution is between 10 and 11. So this is how we can use a variety of indicators and a pH table to help us determine the pH of a solution. One last note is that there's a transition range for each indicator that you might see. And when you have a pH at a transition range, the colors mix. So let's try an example of 5.3 on methyl red. If I take a look, 5.3 is right about here. And 5.3 on methyl red we see is half red, half yellow. Well, what color happens when you have red and yellow? Well, it turns orange. All right, that's all. Have a good day.